Welcome to the Pod of Asclepius, your healthcare technology podcast for the technical crowd. We're bringing the technical experts of engineering, entrepreneurship, data science, and regulation straight to your earbuds. And here's your host, Glenn Wright-Colopy.
Hey folks, welcome back to the show today. Our guest today is Professor Dave Hunter from the Penn State Stats Department. Now, Dave has a very rich, enviable podcasting voice, as I just found out while talking to him before the show. And he's going to be using it to tell us about network approaches to disease modeling, and then about all the cool stuff that's going on at the Symposium for Data Science and Statistics, which is coming up in May. This is the first of 2 episodes on the life science aspects of SDSS 2020, and the next one will have Stephanie Hicks from Johns Hopkins University. So if you'd like to hear when that episode comes out, don't forget to click that subscribe button, and also leave a like and a comment while you're at it. And with that, welcome Dave. Why don't you tell us a bit about yourself and your research?
Well, my name is David Hunter, and I'm a statistician here at Penn State University. This is my 21st year at Penn State. I was the department head here at Penn State until the summer of 2018. And since that time, I've continued to do some of the things that I was involved with as department head, not least the involvement in Penn State's data science efforts campus-wide. And as something related to that, I agreed, 2 years ago or so, to serve as the program chair for SDSS 2020 in Pittsburgh. Jim Harner was the one who recruited me to do that, and I guess we're getting pretty close now to that time, right? It's coming up this June.
Yeah, it's definitely coming up, and I'm really looking forward to the conference. Before we delve into the conference and all the cool topics that we're handling at SDSS, I thought it'd be cool to talk a little bit about your own personal research interests. I saw that you work a lot in networks and various types of statistical inference. Could you tell us a little bit about that?
Absolutely. My dissertation work was actually sort of related to EM algorithms, and lots of people who work in statistics will recognize EM algorithms. And I worked on something called MM algorithms, which is, like I said, an extension of them. And so since my graduate school days, I've considered myself a bit of a computational statistician. Early on in my career here at Penn State, I got hooked up with some folks who were interested in studying networks in the context of how diseases spread across social networks. And so I've also been involved with modeling of networks for about the last 20 years. And then finally, I also got hooked up with a slightly different research group early on in my career at Penn State, and we were thinking about things called mixture models. And so those 3 areas, the algorithms, the network modeling, and the mixture models, are a pretty good synopsis of what I've been working on for most of my career since I got here to Penn State in 1999.
And for those who aren't as familiar with, for example, network modeling, what are some of the main application areas of network modeling? What are the types of data in which a network type model is particularly apt?
I can talk a little bit about some of the stuff that my colleagues worked on. So, for instance, if you're interested in studying the spread of sexually transmitted diseases like HIV, and one of the main modes of transmission is something that you can model as a type of connection between pairs of individuals, for instance, sexual intercourse, then you can try to capture the full population level portrait, if you will, of all of the sexual interactions that occur in that population. And once you have a reasonable statistical model that allows you to, for instance, simulate realistic networks across that group of people, then you can do things like drop an infection somewhere and see how that infection spreads across the network. And once you have this kind of mechanism in place, you can play around a little bit with some of the parameters of the model and see how they influence the spread of epidemics. You're sort of interested in trying to figure out whether there are particular ways that you can attack the spread of a virus like HIV.
That's really cool. I'm a bit curious. So it seems like for the networks, you developed this a priori representation of how the disease spreads, for example, pairs of sexual partners. And then I guess and then you talked about different ways you could look at the sensitivity of parameterizations of that model. Where does the data come in to actually assess the network? Is that once you've created a network and sort of let it reach a sort of a steady state or an equilibrium state that you compare it to real world data? Or does the data actually come in to help you parameterize and actually fit the network model to begin with?
It's actually a little bit of both. And so we start with data on observed networks that we may only partially observe, but as long as there's some information in the data that we can use to understand the formation of networks, then we can use those data to try to fit those parameters for the models that we develop. And we can also do things like try to understand which parameters are important in the first place. And so as I said, you're hoping that you're going to get some nice network observations so that you can inform the models that you're trying to fit. Unfortunately, of course, it's a little bit difficult to get snapshots of an entire population and their sexual activities. And so some of the things that my colleagues at the University of Washington and other places are working on is how you use data that are slightly easier to obtain, such as survey data about people's numbers of sexual partners. And in some cases, if they can name some of their sexual partners, and then the researcher is able to follow up with some of those partners to learn a little bit about numbers of sexual partners of those who were originally paired with somebody that you started with, you can start to learn a little bit about the kinds of properties that will allow you to fit these models. Then, as you mentioned, you also can, once you've got a model for a network, simulate a random network, drop an infection on it, and then see whether the infection, as it spreads across the network, replicates the sorts of things that you actually see in, let's say, disease outbreaks that have been observed in the past.
And I'd like to talk a little bit about how people then take these models that you fit or derived from data and apply them to making decisions with regard to interventions and things like that. But first, I was just a little bit curious. Back in, I think it was the early to mid 2000s, something called scale-free networks were all the rage in a lot of network modeling. Is that related to this work at all?
Yes and no. We are able to, using some sorts of parameterizations, obtain empirical network properties that make things like this scale-free property. But a lot of the literature in the early 2000s on scale-free networks used a slightly different way of thinking about what a network model entails. And turns out that there's not a lot of overlap between some of that work, which tended to appear, let's say, in the physics literature, and some of the network models that we were using to model social networks. It turns out that the number of people working on social networks is huge. And sometimes, as I said, they sort of operate in disparate academic communities.
Could we talk about that a little bit more and maybe how, for example, statistics helps identify the differences between these networks? So first, maybe just define what the sort of scale-free properties are, and then how for example, the AIDS transmission models that you're talking about diverge from those and sort of how you assess that divergence.
So I guess I would first start off by saying that we're looking at in a sort of an HIV transmission type of network has completely nothing to do with the scale-free conversations that were happening. So with regard to scale-freeness, this is an empirical observation that typically if you see a social network, in other words, you are actually able to measure the network of connections among pairs of individuals, what you notice is that there are a few individuals that have a lot of connections to other people. And the patterns that you observe are not at all what you would expect if, for instance, the edges that form between people or the connections that form between people are independent of one another. Instead, you really see this phenomenon whereby, let's say, the rich get richer. In other words, people who tend to be connected already in the future absorb many more connections. In fact, there's a very well-known model by a couple of physicists, including one of my colleagues here at Penn State from the late 90s, that showed that if you are able to assume rich get richer in a mathematical sense, you can actually mimic scale-free properties where you have lots of connections for a very few individuals, whereas most individuals have kind of an average number of connections.
What are then the properties that you're seeing in these AIDS transmission? Like, what are the sort of the statistical properties that you're observing person to person?
Right. So in a disease transmission setting, we tend to be less interested in features of the network, such as whether or not you have a scale-free distribution of what we would call degree. And just as a technical side note here, degree refers to the number of connections that an individual has. And so if you think of the entire range of degrees of the nodes in a network, some of those nodes, those people will have many edges or connections. Some of those individuals will have few edges or connections. And if you look across the range of nodes, you will see an entire distribution of these numbers of connections. That's called a degree distribution. So back to the epidemics, we tend not to be as concerned about things like degree distribution. We're more concerned with, for instance, the prevalence of concurrent partnerships. This is something that one of my colleagues, Martina Morris, has been working on for, at least a couple of decades now. And the idea behind concurrency is that if there's a lot of people who have more than one partner simultaneously, this can really increase the rate at which a disease can spread over that disease. And in fact, that this concurrency stuff, although it's related to degree distribution, tends to be a lot more important than the whole degree distribution. So whereas you might have a couple of individuals in a population who have many sexual partners, i.e. that would be sort of a scale-free situation, what's more important is how prevalent these concurrent partnerships tend to be. There are other issues in an epidemic network, like, for instance, how prevalent are ties between members of the same, let's say, ethnic group, or how prevalent are ties between people who are of similar ages. In other words, how segmented does the population seem to be with regard to whom they form ties with? These kinds of questions tend to be more important in the epidemiological cases that folks like Martina Morris have been looking at than the overall degree distribution or the scale-free properties of a network.
That's really cool. And just to clarify, because this idea of the temporal aspect of it or the simultaneity aspect is really interesting. Is that because there's an actual understanding that the physical transmission is assisted by sort of these simultaneous number of connections, a simultaneous number of partners? Or is it more that this is a helpful covariate that represents other aspects that are harder to, like other transmission aspects, like just the probability of transmission?
That's a great question, and I actually don't know the full answer there. Whether or not there's something specific medically or physiologically about having multiple partners that makes disease spread easier is, I think, something I'm not at all qualified to answer. My sense from having heard Martina talk about this is that you don't necessarily have to assume that there's anything additional happening physiologically when it comes to having multiple partners. It's simply the network itself. If you have partners with whom you're basically having sexual relations more or less simultaneously, right, over the time scale at which these things occur, namely over a couple of days, then the sort of the back and forth between partners that occurs can really aid the spread of these kinds of diseases, whether or not there's anything additional physiologically, which, as I said, I'm not qualified to address.
Well, that's really cool. And now onto your work in mixture modeling. Could you tell the audience a bit what you mean by mixture modeling and then how it applies to your research field?
The mixture models, for instance, there's always a very easy tale to tell about what a mixture model is for people who are not familiar with these models. And that is to imagine that you have measured something like human height on a population or a sample of individuals from a population. And we know that height is related to gender. We know that females on average tend to be shorter than males on average. We also know that there's some overlap. It's not always the case that males are taller than females. And yet, statistically, it's a very easy problem to take a set of measurements of heights with no gender labels whatsoever and estimate quite accurately the mean height for males and the mean height for females, even without being able to identify for a particular height whether that's a male or a female. That's actually a separate question. But estimating means for males and females, along with other statistical properties like standard deviations of males and females, turns out to be a very easy statistical problem to handle. And when you observe heights like this, and you don't observe labels, but you believe that there are labels that exist, then trying to learn those labels is called mixture models, at least in a statistical context. That's what we would call it. Other folks would refer to this as clustering. So mixture models are a form of clustering.
Well, cool. And are there particular application fields that are particularly apt for mixture models?
Well, I can tell you about some of the work that my colleagues at Penn State were doing. There's a psychologist now retired from Penn State named Hoban Thomas, who was interested about 15, 20 years ago in whether children formed distinct categories in terms of how they learned about certain facts, certain things about the world. And he had these really interesting data where children of ages from something like 3 up to 8 were shown a picture of basically a cup, but it was tilted at an angle. The picture showed that the cup was tilted, and the children were asked to predict what the surface of liquid would be in that cup, tilted at an angle. Now, of course, as adults, we know that the liquid should be parallel to the floor. And so if the cup is tilted, then the liquid will actually look tilted in the cup because the liquid is parallel to the floor and not to the sides of the cup. Sometimes children don't know this. And Hoban was trying to find out whether the data would be able to pick out distinct clusters of children. And it's actually a surprisingly hard problem, it turns out, because we had multiple measurements for each child, because the children were shown the cup at various angles. And some of the angles seemed to be harder for some of the children than other angles. And applying our mixture models to Hoban's data set, we were able to provide some fairly compelling evidence for either 3 or 4 distinct groups of children, and to describe in rough terms how those children approached this cognitive task.
That's really cool. What were some of the examples of those? Like, was it the children use different strategies in order to estimate, or
Yeah,
was it just like raw accuracy?
it's a good question. We can only speculate. I suppose Hoban could speculate about the strategies that the children might have used. All we were able to do from the data is to categorize how their response were correct or incorrect. And what we noticed was that, for instance, there was one group of children who simply clearly knew what they were doing, right? They would always say that the water level was parallel to the floor. But there were other children who seemed to adopt the strategy of putting the surface of the liquid parallel to the bottom of the vessel, whether or not the vessel was tilted. There were some other children who seemed to be a little bit unsure when the vessel was tilted at a pretty extreme angle, but they seemed to understand what the true value or the true level should look like when it wasn't tilted at a very extreme angle. And like I said, the fact that we were able to describe these different behaviors qualitatively may or may not point to some underlying psychological strategies that differed among the children, but at the very least, Hoban said that it was interesting, and the statistics that we used were certainly interesting. The methods that we had to develop to analyze these data were certainly interesting.
Well, now I'm a little bit concerned about how I would fare in comparison to these kids and which group you'd put me in.
Well, maybe we can get you tested on this particular task someday.
Absolutely not. Well, Dave, that's really cool. And now moving along to the SDSS conference, I've been a big fan of the conference every year. It's a really good combination of both just practical aspects of data science and statistics, but also getting familiar with some of the still advancing cutting edge methodology that's happening each year. And it's always great the speakers that you attract because they are very good at communicating, letting you walk away with a lot of the knowledge that they have. And what I'm excited to see about SDS 2020 was that you actually have, it seems like at least 2 really big changes to how you're approaching the conference, 2 new big additions. One was with the previewing technical tracks, and the other bit was that you are expanding all those career opportunities. So a bit you're offering things for the hard skills and you're offering some things for the soft skills. Could you talk to us about some of the new additions for SDSS 2020?
Absolutely. Probably the main thing that's new is that SDSS, because it's trying to bridge the statistics and CS and data science communities, is trying to adopt a profile that makes it look slightly more like some of the big name CS conferences, things like ICML or NeurIPS. And at these conferences, typically what happens is there are thousands of submissions for work that folks will hope to be accepted to the conference. We're trying to adopt that this year at SDSS through refereeing the contributed sessions. And this is the first time, as far as I'm aware, that this has ever been tried at a statistics-sponsored conference. So the ASA, of course, is sponsoring SDSS. And I don't think that the American Statistical Association has done something like this before. We have solicited about, at this point, 80 abstracts from people who hope to be in our contributed session. And we are probably going to whittle that down to about 50 or so based on the amount of space that we have available. And so the fact that this is I don't want to say competitive, but at least it's a refereed process, does a couple of things beyond just making this look a little bit more like a computer science conference. It gives some prestige to the event, and it helps folks who are trying to add talk to their CV in convincing people that this was not just something that they sent in that wasn't looked at by any referees. This is something that was accepted into the conference. And as I say, we're seeing how it's going to go this year, but at this point, right now, we have just closed the submission period, and we're about ready to launch into the refereeing period. And like I said, we'll probably be accepting somewhere between half and 2/3 of the submissions. At least that's our estimate at this point. And well, that's not close to the 15 to 20% acceptance rate at some of the most prestigious computer science conferences. But it's also kind of a nice place to be. I don't necessarily want us to see us get entirely exclusive. And yet this is a bit of a new profile for the conference, and I hope it goes well.
And one thing that can't be understated is the value that this, curation process has for attendees themselves by requiring that the speakers are a little bit on guard, making sure that they're putting the best work forward, presenting it to the best of their ability. It makes sure that people who travel all the way out to SDSS can make the most of their time. There's nothing worse than basically a presenter coming in and not being ready to put their best foot forward to really communicate the value of their work. But it's amazing what happens when people do put in that effort. So it does seem like it's a good compromise between making sure that the conference is very inclusive, which has always been a nice strength of SDSS, while also saying, we're going to make sure that we're getting the best out there in front for you to use. So your time is well spent.
You're exactly right. The virtue of this new refereeing system is not merely because we're trying to be more like a CS conference. As you point out, there are many other benefits as well. And these conversations that took place among the program committee members when we were trying to decide whether to go ahead with this raised many of the points that you just did. There's value in both making the speakers think a little bit more about what they're submitting and also reassuring conference goers that what they have signed up to see is something that's been judged to be of high quality. So we're optimistic that this experiment will at least be a partial success. We will see what happens, of course, but right now, signs are good.
This year, I believe you're also adding some professional development aspect to SDSS.
Yeah, that's right. There's a couple things that we're instigating this year. One of them is an online search capability so that people can submit their resumes or CVs online and also be able to search certain employers online. This is a new thing that we're trying in conjunction with an event that we're launching for students specifically to interact with corporate representatives. We're calling it a meetup, a corporate student meetup. And we have been aided in this by some of the folks from Carnegie Mellon's outreach office who have a lot of corporate contacts in the Pittsburgh area and beyond. And they think that there's a lot of potential interest from the employer side in interfacing with students who happen to be at SDSS. And so they're going to help us try to make that happen.
Well, it's really great to hear a conference try to meet its attendees' needs more by revamping and innovating from the previous year to make sure that they are staying at the edge of their game. What are some of the good things that SDSS did in previous years that you're going to be taking forward?
In addition to the new career-related activities this year, we're going to keep a couple of things that were really successful from last year. And one of those was this speed mentoring service where folks who are looking for jobs or know that they're going to be looking for jobs can talk in 1 to 2 minute spurts across the table from somebody who's a little bit more experienced, maybe a senior academician or somebody who's senior in industry. This is something that Kelly McConville and her program committee instigated in 2019, and it was a big success, much like the conference itself. And we're going to keep that. And in fact, there are so many aspects of SDSS 2020 that are going to look almost exactly the same as SDSS 2019, which to me is just a real shout out to the job that Kelly McConville and her program committee did last year. It's wonderful to be able to expand SDSS knowing that anything that you keep from the previous year is going to go well. And so that's really given us a chance to think broadly and think about how we might do these things like the meetup or the refereed submissions that maybe wouldn't have been quite so easy if Kelly and her team hadn't laid such a solid foundation last year in the Seattle version of this conference. So thank you, Kelly, for what you did last year.
Yeah, that's definitely true. Having just started a podcast, I know that there's a lot of things that you can fine tune really well once you have a nice base to it. But before you have a nice base, it's a lot of scrambling and a lot of work. So definitely we are beneficiaries of the people who came before us.
Absolutely.
And so one other nice thing about the conference that is obviously different from last year is that it's in Pittsburgh.
So yeah, Pittsburgh is an exciting place to be. Nothing against Bellevue as a location. That was also beautiful last year. But we're moving from the West Coast almost all the way to the East Coast. And the location is wonderful. The conference venue is a hotel that's right next to the Point, as it's called in Pittsburgh, which is the conjunction of the Allegheny and the Monongahela rivers to form the Ohio River. And it's a beautiful central location right there in downtown Pittsburgh. And I believe it's something like a mile from the hotel if you were going to walk to the Point, which is definitely something to see. We're also right across the river from PNC Park, which is where the Pittsburgh Pirates play. And fortunately, it turns out that there is a home Pirates game every single day that the SDSS will be taking place. I think it's from Wednesday to Sunday. They have a long homestand. In addition to baseball, if that's not your cup of tea, it turns out there's lots of other stuff right on the other side of the river. The Andy Warhol Museum is over there. And of course, downtown Pittsburgh itself has all sorts of restaurants. We are right near the theater district at the SDSS conference venue. We are about half a mile, if I'm not mistaken, from something called the Strip District, which is a bunch of trendy shops and restaurants. Easy walking distance from the conference venue. So it'll be an exciting place to have a conference. And I will say that we listened to some of the suggestions that conference attendees made last year when they asked for just a little bit more downtime. We've intentionally not scheduled quite as many events for this year's conference. We've left more open time, mostly in the evenings, so that if you're here in town or if you're in Pittsburgh to attend the conference, you get a chance to get outside a little bit and just see what downtown Pittsburgh is like in the summer. Beautiful place.
Well, I'm just going to have to make one addition to the list that you just described. It's, of course, the University of Pittsburgh Medical Center, which is one of the nation's premier medical research institutions. Maybe not the tourist place that everyone wants to see, but they give a lot of good data that a lot of people use. So I think that's a locational highlight as well.
Well, and there's going to be a lot of biostatisticians in this group, Glenn. So I think a lot of them would appreciate the plug for the Pittsburgh Medical Center. So.
Yeah, and on the topic of biostatisticians and life science in general, we are going to be following this episode up with an interview with Stephanie Hicks, who will be talking about the healthcare and life science aspects of the upcoming conference.
That sounds great.
Well, Dave, thanks so much for your time today. I really appreciate it.
It's been my pleasure. Thanks for calling.
Well, that's it for this episode of the Pod of Asclepius. We hope you enjoyed it and will tune in for our next episode. If you're watching from YouTube, don't forget to subscribe to our channel and leave a like. You can also follow us on our other social media channels, including LinkedIn, Twitter, and Instagram. Have a great story or presentation that's ready for prime time? Or know someone who does? Drop Glenn an email because he'd be happy to hear from you. We would like to thank our sponsors from the American Statistical Association section on Statistical Learning and Data Science, section on Medical Devices and Diagnostics, and North Carolina chapter. The views expressed on the show are those of the speaker and not their employers, our sponsors, or anyone else not saying the words.